All right, good afternoon and welcome to our monthly Firefighter Cancer Initiative. This is month 2 of 12 of our FCI annual meeting. We're going to give a few minutes for folks to settle into the webinar room, and we'll get started in just a few minutes. So feel free to adjust your volumes and orient yourself on the webinar. And in a few minutes, Dr. Sally and I will introduce our guest scientists and get the webinar going. So welcome to our FCI seminar series. If you can hear me, you're in the right spot. We'll be talking about firefighter cancer prevention during this webinar. So we will introduce our guest speaker in just a moment. So feel free to settle in, adjust your volumes, and we'll get started. Okay, so why don't we go ahead and get started in the interest of time and also to allocate space at the end for our question and answers. So happy Wednesday, everyone. I want to welcome you to our second year 10 Firefighter Cancer Initiative scientific seminar series. This is where we devote some time to ask one of our scientists to present an update on research of the topics that are most interest to our firefighters. Today, we have a really special scientist with us, Dr. Pratim Biswas, who is the Dean of the College of Arts and Sciences. And before I formally introduce him, I just want to say it's so great to have him here at the University of Miami. He is an international scientist known for his work in aerosol sciences and was so warm and welcoming to our idea of working together on identifying, and characterizing the risk exposures of firefighters through aerosols. As you all know, first responders are exposed to a whole heterogeneous plume of different contaminants when they're on the fire scene or doing training exercises. And the ability to be able for us to characterize those exposures, those aerosols that are present there using the latest technologies is really important to us. And this is really what Dr. Biswas and his team bring together. Over the last couple of years, we've been able to share mentorship with one of our amazing PhD students, Dr. Shruti, who will soon be a doctor, but has been training with us collaboratively on these projects, and I'm sure you'll hear about them this afternoon. So please join me in welcoming Dean Biswas. His research and educational interests include aerosol science and engineering, nanoparticle technology, air quality engineering, environmental benign energy production, and even environmental nanotechnology and public health, which really what brings us together through the Firefighter Cancer Initiative as we try to address occupational exposures to our first responders. So please join me in giving a warm welcome to Dr. Biswas. I'll pass it over to you.
Okay, thank you, Alberto. It's a great pleasure. Thank you, Natasha, too, for setting this up. I'll give a sort of exposure to some of the work that we are doing with respect to the Firefighter Cancer Initiative. And this has been just fabulous for us because it also brings relevance to such an important problem and to helping some of our, in some sense, first responders and trying to keep them safe. I'll be talking about some technology push more on the physics-based side of the data also through case studies with some novel instrumentation which our group has been developing. So first, before we forget, we get to make these very interesting presentations, at least from our perspective, but it's those PhD students who have really done all the work. And Shruti was mentioned. I have to single her out she might as well been giving this presentation. I, of course, got some of the data from her, which I'll be presenting. And the group is broad with a lot of agencies funding us, and we find this very exciting. So I should also say my lab is called AAQRL, Aerosol and Air Quality Research Lab. At Miami, University of Miami, we have something called CAST, Center for Aerosol Science and Technology, which includes public health experts, colleagues from the Rosenstiel School, and of course the engineering school where I am located. So in terms of an outline, and please pardon me, there are many experts in the audience, but I'll still give an aerosol primer, and just bear with me, or even later give me feedback if I missed something basic. I want to talk about that to just put the problem in perspective. Then, as I said, I'll talk about real-time aerosol instrumentation. And these days, the concept of wearable technology, in this case, wearable sensors. But most important, I want to highlight some selected results of these studies, which we have been doing collaboratively with the entire team. And Shruti has taken some of these tools out to the field. So I'll talk about those three. And I was very excited to see her also collect some data from EV fires. And I'll discuss that and highlight some of those aspects too. So aerosols, if you look, it's a Greek word. It's very simple definition. It's a suspension of small solid or liquid particles in a gas. So it's very important. These particles are suspended in a gaseous medium. And then, of course, as you know, what is a particle? A particle is basically a stable cluster of molecules and atoms. In this case, very relevant because we are starting with high temperatures, a fire typically. Things are in the molecular state, but then as things are down, they cluster and form these particles. So the particles are rather small, and they cause, of course, in this case, could be problematic, but they are very different from the gas in which they are suspended. So in this case, they'd be suspended in air or maybe some other pollutant gases. So particles suspended in a bed of molecules, and it's very interesting physics. This is what really we breathe it in, for example, what fraction will deposit, what will not deposit. So this, of course, we go into the detailed physics. Today, I'll just focus on characterizing these aerosols, and more so, what do we mean by that? So one, of course, is the size. And I already alluded to how large are they, how small are they. So we can measure the diameter if it's a small spherical particle, or I can measure the surface area, because if I inhale it or if it deposits on my skin, it's the surface that's interacting with the biological tissue, or the volume, which also determines the mass, right? So this is just a metric of size. And then we bring in the shape. Not everything is nice and spherical. While I use diameter, I might need an effective diameter or an equivalent diameter. So these two are important characteristics. And then I put up, examples. And look at the bottom, combustion aerosol. They are in the nanometer sizes. So it's 1,000th of a micrometer is a nanometer. And we all know how large a meter is. You can just spread your arms, and you break it up into million parts, you get a micrometer, and 10 to the 9, and you get a nanometer, extremely tiny. And a very interesting picture of a combustion aerosol with a lot of pores. So it could be a carrier for many things. We are all familiar with the SARS-CoV-2 virus. That is a few 100 nanometers, let's say. That has caused havoc. And that is airborne, so it meets my definition of an aerosol. And then, all kinds of particles, some I could synthesize, and you look at the scale on the right-hand side. And just to get, you can hopefully you can feel some of the hair on your head, and that is about 50 micrometers, right? So you can imagine a combustion aerosol is orders of magnitude smaller. And the concept of shape becomes, we just finished the Olympics. We came back, I think, with 2 gold medals in basketball. That's a nice spherical particle. In Miami, we have to be football fans. The football, as they call it here, football is not a spherical object, but when you throw it, it's, of course, again meets a definition of a particle in flight that's more continuum. These are large particles, but these are some important features, right? So now let's see, another feature is concentration, because eventually I want to know how many of these I have, right? If I'm inhaling it, is it going to cause me a problem? And then we use the concept of concentration, and I'll allude to that a little more. Composition, what is it made up of? I just mentioned combustion aerosol. It could have toxic elements. It could be a heavy metal. It could be a carbonaceous material. It could be a PAH, and so forth. Okay, all very relevant to firefighting scenarios. So let's continue. Concentration, I can just sit and count the particles, but I want it per unit volume. So let's say I use meter cube and I just count them. So I use the number sign. So I have 10 particles in a cubic meter. Or I could also associate it with a mass, because the mass is important in terms of some other effects. So I could use micrograms, and I use these smaller units, micrograms, not grams, not kilograms, not pounds, micrograms, because there are fewer suspended and so forth. And then there are some mathematical relationships. Let's not go in too much into it, but the size distribution function, because for every size I could have a different concentration, and that's shown in the graph. And typically you just step outside, you step or measure the distribution in your room, and you'll see this bimodal kind of feature. So there's a small mode, which again on the x-axis you see the diameter scale. It's rather small units in micrometers. And then there's a larger one. For example, in Miami, we get the Saharan dust. We are next to an ocean, so we get a sea salt spray. Bacteria sometimes are larger, so whereas viruses are much smaller in size. But this is known as a size distribution. And this is extremely important, especially with respect to the health effect. You might have heard of these terms PM. I'll call it PMX, but we are familiar with PM 2.5, PM 10. Knowing the distribution, I can calculate these and so forth. But 2.5 refers to, PM 2.5 refers to the mass concentration of particles smaller than 2.5 micrometers. Of course, you'll say, why do they choose 2.5? This is something related to our health and safety. If I inhale it, it has to be below a threshold level, and that is the basis of regulations. So that's why I sort of pick on PM 2.5, PM 10 is smaller than 10, but it's the finer particles, again, things that come from fires, combustion, burning, they are smaller. So that's why we use the smaller metrics to characterize it. So PM 2.5, let's remember that as we go along in this presentation. Why is this even relevant? Now I am sitting here, all of you are breathing. I am, of course, excited when I talk about aerosols. I'm breathing a little harder. I want you all to be excited, or if you go running after my presentation and come back, you'll be breathing harder. But a normal adult is just breathing a large volume of air, breathing out. And with it, all these particles are entering my respiratory tract. And very interestingly, they deposit in different regions based on that size. So this graph tells us what fraction would deposit at different parts. And I've just used three, the head region, which is the upper tract, the bronchioles, the bronchi, and then the alveoli, right? Alveoli is deeper into the lung. And if you look at the SARS-CoV-2 virus, it deposited in a specific region of the respiratory tract, which allowed it to be uptaken and then multiply and cause disease, right? So these are all very relevant. And same with the firefighters inhaling something, or even individuals inhaling, what fraction would deposit. There's not everything bad associated with this. For example, if I want to deliver things into the brain, there are olfactory nerves, and you look at the head region. So very small particles would deposit in the head region, what I refer to as the head region. It's basically the nostrils and the mouth. From there, there are a bunch of olfactory nerves, especially the nostrils, leading to the brain. So I can translocate particles into the brain, for example, right? So if I want to treat a neural disease associated with the brain, I might deliver drugs that way. Respiratory illnesses, we often take in an aerosol. So something that causes a problem could also be turned around and used to maybe remediate or deliver pharmaceuticals to treat a certain problem that we encounter. But based on this, there's a whole bunch of regulations. Again, busy slide, but let's start with the United States. US EPA mandates that PM levels, this is PM 2.5. Okay, I should have said PM 2.5. On an annual basis, the concentration has to be less than 9 micrograms per cubic meter. So this is an annual average, right? But why do I wait for the whole year? And they also have a 24-hour average. So if Miami suddenly gets a burst of wildfire aerosols, for example, or there's some kind of release, the concentration on a 24-hour average basis should be less than 35. This is mandated. If it exceeds this, we are violating the standard, and then the EPA might really require us to take some action about it, right? And these are all associated with adverse health effects. Now, you might be extremely healthy and say, hey, I can take a higher level, and that may be indeed true, but these are for the sort of the most compromised individuals in society, which are children, elderly people, and so forth. And a standard, of course, reflects the entire population and so forth. WHO, which is an international body, the World Health Organization, you will see that their levels are a little lower. And they do their studies and they find out that, hey, the threshold is lower. Now, let's come to firefighters. We, of course, are exposed, maybe on a 24-hour basis, but there's also a lot of acute exposure, which means I go in to fight, let's say, a wildfire, and then I'm exposed if I'm not wearing the right equipment or after, and I'll come to case studies later on. We have a major issue, and it's an acute exposure, right? I can't look at the annual average because I might not be doing this all through the year 24/7, right? So unfortunately, acute exposure standards are very few, but there are some. So the Agency for Toxic Substances and Diseases, part of DHHS, says that let's use the 24-hour average standard for a 1-hour average. So if a firefighter is going to fight a fire and is exposed to more than 15, that's problematic. Okay, that's a guideline. And now you go to the mining society, people who do mining, they are exposed to dust, and you see that they have a much higher PM threshold level on a 1-hour average basis. So these vary. OSHA, in occupational environments, I go to work, I'm in a dirty environment, and you see that it's in milligrams per cubic meter, so much higher level, but this is for non-regulated PM and dusty environments. And then there are also recommendations for firefighters and things like that. They use something called a respirable exposure, which is PM4. Remember the PM 2.5, which is for ambient. They refer to PM4. We all disagree with respect to what to base our standards on, but the PM4 is 1 milligram per cubic meter for a 10-hour kind of average exposure. And if it's 14 hours, it comes down a little bit. So it goes all over the place, but the net is it's well understood that PM exposure causes adverse health effects. In fact, for continual exposure in the ambient atmosphere, it's resulted in excess mortality, right? And it's one of the highest after, I think, cardiac diseases. Death due to air pollution exposure is way on the top. So this is a very serious matter and should be taken extremely cautiously. Should we have better standards for individuals such as firefighters or occupations such as firefighting? Absolutely. More work needs to be done, and more specific details need to be developed and so forth. So that's one message to take. And I'll just back off a little bit again and come to AAQRL. Aerosols could be good and bad. Today, of course, I'll refer to the problematic particles, but the same knowledge can be used to make all kinds of good particles. In fact, I'm going to talk about EV fires, electric vehicle fires, at the end of the talk. By the way, batteries are getting better and better in terms of performance. It's surprising. You'll note that the electrodes, some of the battery materials, they're made by aerosol processes. So just look at the contrast. In one case, an EV fire is problematic, maybe, but then I make the battery material. Can I use the knowledge to make better batteries which are also safe, which keep individuals such as firefighters, users safe? So on the right-hand side, you'll see drug delivery, battery materials, nanomaterials. These are all purview of our group. And anyone, I don't know how many of you are listening here. I heard a sizable number. You're most welcome to visit our lab on our beautiful campus in Coral Gables. And I'll volunteer Shruti or the other students or even myself. We're happy to show you some of our things. And at the bottom, it's a very fascinating field with all kinds of applications, even for agriculture, commodity, powders, and so forth, right? But let's come back to this. I'll switch now to aerosol instrumentation and wearable sensors, and then want to get to the case studies. So, I told you there are standards. How do I know I'm meeting a standard? So EPA mandates that we actually measure the PM levels out in the atmosphere. Miami has about 6 stations. I think Miami-Dade County, the greater Miami might have more, 6 stations where these are continuously measured and reported. And you can look up the EPA site and you can find out the PM 2.5 level yesterday, for example, right? These devices are not that expensive, but reasonably expensive. They're bulky, so they're 1 meter tall. Of course, they're anchored in these stations, and they're constantly measuring. And these are known as federal reference methods, different types of instruments that are put out there. Then you come to our lab. We want fancier stuff. We want things which operate more on real time, which can measure smaller particles much more accurately. So there's an instrument known as the Scanning Mobility Particle Sizer. Look at the cost. It goes way out of the roof. Of course, you might say, hey, that's not that high. There are $1 million instruments. But for us, these are workhorse instruments, and it adds up, right? You come into our third lab where about 3 or 4 of us faculty members have our research groups. There might be 4 or 5 of these instruments floating around because this is a workhorse. And Shruti occasionally takes this out to the field, but it's bulky, right? It's sensitive. It needs love and care, and it needs individuals like Shruti to take care. So there's a push to make these things smaller and that we can carry around. And Dust Track is a commercially available instrument, not as accurate as the ones above, but a lot more portable, right? But still $3,000. Not all of us are willing to buy one and carry it around. While it fits in my palm, it's not convenient to carry around. I always look at my iWatch or whatever this is called. It measures my blood pressure, blah, 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 everything. Gives me the time also. That's the kind of things I want. So there's a big push to bring down the cost further. And there has been literally a revolution. This is a startup some of my former PhD students created, and we still use their sensors, applied particle technologies. It's real time. It sends the data to the cloud. I can sit in my office and see what someone is being exposed to. And these are also wearable and so forth, right? So these are the two instruments we used in these studies. A little larger one made by Grimm, that's just a manufacturer. On the right, it's based on light scattering. So whenever a particle comes into a region where it's struck by a laser, by laser light, it scatters. That scattering signal is a reflection of the size of the particle, right? I can then modify this. I want to know more about the particle, the composition, and so forth. And by counting how many hits I get, I can also get the concentration. So in some sense, rather simple, but optical devices are becoming cheaper and smaller. And again, lot of credit to technology development, which allows us to make these more and more compact. And on the right, you see that wearable sensor. Again, it's rather tiny and it's been clipped onto a firefighter's jacket, right? So now we can literally follow the firefighter and see what the device is measuring. We could even put one inside the SCBA, self-contained breathing apparatus, to actually see what the firefighter is inhaling. And you could measure inside, outside the face mask and tell the difference. So it really makes things possible to do now, right? And it's really caused, I call it a social revolution, the concept of a smart city, not just firefighting. I can put these on drones, I can put it on a robot, I can put it on a fire truck, I can keep it in my office. In fact, I have some in the office. I could wear one and walk around and really get a good map. At the same time, there are satellites which are beaming down on planet Earth, and I can use satellite information to also get estimates of these particle concentrations. So a lot of technology development. Now let's see in the remainder of the time a few case studies, and some of you might already be familiar with this. And these are all data collected by Shruti. And I'll talk about a controlled burn, a training center which allows us to deploy these in a rather non-intrusive manner, or somewhat intrusive. But thank you again to all the firefighters who allow us to really come in. And hopefully we can, of course, not only tell what you're being exposed to, but minimize that, right? Then longer term exposures and the bunker gear. And this is something we found out as we were doing these measurements, I think, and I learned new words myself. Doffing is taking off this gear. And I think you come from a hot environment, you want to really get these things off. But then what does it do? And then, of course, very interestingly, very recent, these electric vehicles and intentionally creating a fire and seeing how we can handle these things. Okay. So I'll first talk about this training site, just a fabulous site. It's a room, basically 8 feet by 25 feet by 12 feet high. You can have a fire in there. Could be initiated with hay, with whatever material you want. And this is also interesting. Rooms like this allow you to test out different material burns. Like you might have maybe a concrete fire, you might have wood fire. So each will give you some differences in the aerosols. We identified 3 regions. One is inside the room, because the firefighters are doing their training, their things there inside. And you see those stars, those are where we put these on to certain firefighters. Maybe we could also keep it stationary. So the Grimm, the big, slightly larger device, was it's not moved around. It's fixed in a corner, maybe far away from the live fire, so that it's not burnt out itself, but it's also measuring. Then the region outside the room, there's a door, people want to come out, and so forth. And then what we refer to as a faraway zone. And these are just arbitrary terminology in some sense. Inside, outside is near vicinity, and then far away is just a certain distance, 100 feet away, not that far away. But there are also firefighters there. Inside the room, as I mentioned, they wear self-contained breathing apparatus. That's obviously required. And there are, of course, safety procedures and things that are followed, but we still wanted to have a good understanding of these things, right? And we measure at all those three locations. So let's look at some of the data. So just having these sensors, we can track someone around. They set up a fire close to 9 a.m. or slightly after, and the red line is that the PM concentration on the y-axis in microgram, PM 2.5 micrograms per cubic meter, and the x-axis is just as time, and I'm plotting it out, right? And my sensor is detecting it, and Shruti, using her laptop, is actually seeing this as it's happening. So, so the fire is started. Obviously, there's a burst in the PM 2.5 going extremely high, right? It's a real fire. It's a sort of enclosed environment. And remember the standards I talked about, 15 micrograms per cubic meter. Okay, 35 micrograms per cubic meter. Look at this. It's touched 4,000 micrograms per cubic meter. So no matter what, that can't be a safe environment. Obviously, they are wearing their SCBA, highly recommended, but also well fit and well designed SCBA. Then let's say the firefighter wants to come out, whatever reason, or they're just doing an exercise. They open the door, and the green symbols are outside the room, right? We have a sensor outside. So there is a burst outside the room, right? Normally it's quite low, but then there's a burst because the door has been open and some of the particles are just coming out. And of course, this firefighter probably came out, and also you see the concentration drop with the wearable sensor. And then maybe they go back in, and this time they open the vent. So if you saw that, there's a vent maybe to leave out the stuff. And these are all good because you can do different scenarios. And there's a slight drop. There's a significant drop, but still extremely high. So if you just rely on a single vent to maybe clean out the room, that's not sufficient. That's what it's telling you. And then again, the door is closed and so forth. Ultimately, the firefighters just come out of the room. And you can see that when the door is open, again, there's a burst of concentration outside the room. And the wearable sensor with the firefighter is dropping, but still, I would keep repeating, extremely high. 2,000 micrograms per cubic meter is a high level. And of course, then with time, this drops off. So this allows us to really get data on a real-time basis. A supervisor could be tracking, and no matter what, if they're wearing SCBA, you might want to rotate some of the individuals out and come up with a strategy and so forth, right? And if everyone has one of these, you have that capability of even designing a scenario of tackling the fire. Let's look at some more. And this is now the size distribution. That was just PM 2.5 with time. This is now the size distribution, which means the concentration on the y-axis plotted as a function of particle size. And before you start the fire, its background, it's quite low. That's the green dots. Then outside, it stays low because the door is shut. The concentration is rather low. And then inside, of course, you see there's a burst. But the particle size is somewhere between 200 to 500 nanometers. So these are very tiny particles, very much expected in a combustion system and so forth. And then on the right-hand side, they come out. And when they take off their gear, right, when the gear comes off, the size distributions, the scale is way smaller in terms of the concentration, but it's still significant, right? And it's in that certain size range. And and then way after the training is done, the concentration drops off. So it takes certain amount of time. There's a very interesting thing to note when they take off their gear. Inside the training room, they're wearing SCBA. When they're taking off their gear, everything is stripped off. Now you're breathing the air in your surrounding. So just to plot again, where does all of this deposit? I just illustrate that. That's the region. So most of the particles are in that size range. And you can see that, oh, you'll say the deposition, a smaller fraction is depositing, true, compared to other sizes, but still a significant fraction is depositing in the alveolar region, right? So it's still penetrating, and one has to be rather cautious as to the breathing patterns later on. I won't talk too much about chemical composition. We also have devices to now collect these particles. Unfortunately, our sensors only give a concentration level, but we would like it to give us, the composition, means what is it made up of? And Shruti is actually designing new sensors to allow us to do some of that and also detect things like viruses, bacteria, pathogens that are airborne. And she's doing fascinating work. But here we collect these particles in different size ranges. Again, where we see most of the pHs, they are exactly matching the size ranges were highest. And these are rather high concentrations. This is, of course, inside the training room. And you see there's all kinds of pHs, 6 rings, 5 rings, 4 rings, and some of the higher ring components are more toxic. Several of these are carcinogenic, so you don't want even a small fraction to be inhaled, but the concentrations are rather high. And again, the strategy, what is done, how you actually tackle a fire, these can all be used to derive some of that, not to mention, what is maybe an exposure and how can we keep the firefighter safe and things like that, right? So the next case study is now taking off the gear. And on the left-hand side is a picture of a fire department. You come out, this tent-like structure, you just take off your jacket and throw it down and start cleaning up. Allows us, because it's a nice tent, you see our instruments on the cart, we roll in our cart, we are waiting for these individuals to come in and go through this doffing procedure, and we are measuring the size distribution, right? And we want to see how does it compare to the background levels. And this is important too, because as I said, they're taking off all their protective gear. There is something known as a decon process, which means I think it's washed down before they go in to take off their gear. That is done sometimes too. And we can compare no decon to with decon and so forth. So the red line is the size distribution again for a fire with no decon. And this is during taking off the bunker gear, right? And the black line is with that some kind of a decon process. Obviously, it's lower, but it's not significantly lower, right? And then different kinds of fires, you have different kinds of aerosols and particles, and they stick and you get different distributions. In case of fire 3, the decon didn't result in a much lower concentration, but you look at the background, the blue line at the bottom is the background. So we are way above the background levels. Now, if you're not wearing any kind of protective gear, one has to really be cautious. How long does this stay on and so forth, right? So we also have to do a temporal analysis in some of these bunker gear doffing chambers or wherever this is done. Sometimes it might be done in the open. Do you do it quickly and move away? So all kinds of strategies could be developed just based on some simple monitoring data. The other thing is now the firefighter wants to go home. You return in a fire truck shown at the top, and you might see those 2 arrows and those 2 rectangular boxes. One is in the driver's cabin, the other is at the passenger or the back, right? People sit there. Many times they toss their fire gear into this kind of region. So we just wanted to see if is this continuing, the exposure continuing even as they're driving away and going back to base or wherever they're going. And sometimes they drive their own cars, right? And we can give them one of, so this gentleman is holding our sensors, if you look at the bottom, and we were again very grateful for them to allow us to do these measurements. This is just a summary inside the fire truck. Look at the first in the fire truck, the mean PM 2.5 could be rather high, right? It's way above maybe even the safety limit, and now you might drive for 1 hour, half an hour, or you're taking it home. I don't know where you take it and stuff like that. And then we also measured PM1, which means particles smaller than 1 micrometer, because that ultimately is the one which might be respiratorily problematic. And then we also got data for a personal vehicle. A personal vehicle, maybe the concentrations were much lower. It, of course, depends on the doffing, the gear that is taken off and carried. But also maybe the air conditioning, the air exchange is much better. So it's not that these levels would always remain. There are strategies. So you see here that the PM 2.5 levels decrease with time inside the vehicle. And this data was shown at the end, like it's 15 micrograms per cubic meter, but initially started off maybe at 30. And very quickly, in maybe 20, 30 minutes, it drops to this level. And same on the right-hand side, where it was much higher, but then the concentration drops down. Could be with the ventilation, could be with an open window, many reasons and so forth, right? Okay, final example, my last one is on EV vehicle fires. This car to some will start looking not so familiar, but is a standard gasoline car, and the lady's hand is on top of the battery. It's a small battery. I've of course shown you a sketch on the top, and it's a lead acid battery. It's made of toxic constituents, but it's mainly metals. It's away from the engine. It of course might get warm, but rarely does it catch fire, right? And so forth. So they're relatively safe, at least with respect to the battery. We of course carry gasoline, which is another issue. Look at the counterpart electric vehicle. I think the bottom is a Tesla, top is also, I think. The entire bed right above which you're sitting is the battery, because now that's my only source of power for the vehicle. It covers the entire vehicle. So it's a large area, large volume. It's most of the weight. There's no engine now to deal with, no gasoline to carry. So it's, and these are specialized batteries. It's not the good old lead acid battery. It is a lithium ion battery is the most common one these days, with new designs coming up. If I look, it's not only cars, electric vehicles. Soon we are going to have cars which are going to start flying. And these are not helicopters, these are cars, electric vehicles which will start flying. And it's vertical takeoff and landing. I moved here about 3.5 years ago, still complain about the traffic. And I don't know if I'll get used to it. But just imagine I hit a traffic jam, my car takes off vertically, comes and lands behind engineering, my office, also vertically. And Miami, there's tremendous action happening. We have a consortium here. But the thing I mention is just imagine a flying car having an electric battery, right? It has to be robust. I don't want it to come crashing down. So it's much higher capacity batteries that we have to now design and so forth. So a lot of these are coming in, and of course, there'll be landing sites, there'll be takeoff sites, and these all are going to require to be extremely safe and fireproof. We have to store batteries because I have to swap them out. if you look at the design of a lithium-ion battery, there's lithium, expose lithium to air, oxygen, or even moisture, it's going to combust. It catches fire. On the other hand, the other electrode in orange is a carbon-based material. So if this heats up and sort of ignites in any way, the carbon is a fuel, right? It promotes the fire. So it's completely made up of combustible components. Why do I even do that? Being now a nanomaterial scientist, can I do better so these things don't just go haywire and once they heat up, they'll catch fire, right? But this is what we are using. And the cars are not flying yet, but the top is very prevalent and so forth. So in fact, today's New York Times, I look at South Korea, there was a big Mercedes-Benz electric vehicle fire and it in a parking lot just by itself, right? No one hit it, no one did anything. Something went haywire, some defect, and it caught fire. It's in today's New York Times, right? And South Korea is beginning to question, should we pause using electric vehicles? The US House had a hearing on electric vehicles fires and, regulations, training, they say that technicians should have training to take care of these systems. And what is it that causes the fire? It is this battery. I told you about oxygen exposure, heat. There could be some fuel. If it's a hybrid, there's short circuits. There's high temperatures, very common here in Miami. Charging, discharging cycles, all kinds of things. So people are beginning to understand these better. And then there are people who'll say, hey, look at the fires in gas vehicles, gasoline vehicles. It's way more per 100,000 vehicles. More, of course, more in hybrids compared to gasoline, but the total fires in gasoline vehicles is an order of magnitude, 199,000. Of course, there are so many more gasoline vehicles going around, but hybrids and electrics are going to go up. So this is the time. But more importantly, the responders, like firefighters, have a great challenge. A large amount of water is needed. The characteristic of the fire is very different from a hydrocarbon fuel or a gasoline fire, right? You need large amounts of water. And if it's happening in some corner, just having that access to all of this is extremely important. Okay, let's look at some data, just like we did PM for training sites. We want to, and we were just delighted that individuals were doing this test. Now, instead of a training site, you have an electric vehicle that they want to set fire, and they did it by heating it. The firefighters were all around it. So we have a hot zone, a warm zone, and a cold zone. Again, just a simple terminology with distance. And there were individuals labeled A, B, C, D all around this and actually handling the fire, getting trained, and so forth. Okay, but this allows us, let's get our devices, measurement devices, and put it on. So let's put the one and track the one closest to the burning electric vehicle. And you see that the green is where the fire is initiated at 10:21. And you see, again, large spikes. And these spikes are also rather high. It's just like the training, enclosed training room. 2.5 would go as high as 3,000 because the entire vehicle starts burning, and it's up and down. That might depend on the wind pattern or the firefighter moving around a little bit. And then the firefighter, flame suppression begins and the concentrations drop off. But then again, doffing of gear, there's a peak, and then aerosol resuspension. These are actual measurements, and these are quite new. I think they happened a month or two ago. So we have to still analyze this. We are also looking at electron micrographs of these particles. You definitely need respiratory protection all the way around and so forth. And it's also sticking to the gear, right, that the firefighters wear. This is now a little away, 50 feet away. Sensors B, maybe on firefighter B, very similar. A little lower, maybe. It didn't touch 4,000. It's touching 2,500. but same kind of thing. And you see that during doffing, the resuspension from the gear, these are all following pretty much that training site kind of scenarios, right? And but these fires could be much more extensive, and then of course putting them out, as I said, you might need a lot more water. And what is the composition of the particles? That is, we see a lot of heavy metals in the particles with our preliminary electron micrograph analysis. Of course, a lot of carbonaceous particles too. And then 100 feet away, again, concentrations go up. This depends on the direction of the wind, and 100 feet is not that far away, but you see that a spike would happen. Relatively fewer spikes compared to the ones closer, but still reasonably high. And again, here also you have to have protection, and that's pretty obvious in some sense, but always important to even repeat things. Oh, I'm a little further out, let's not wear all that, but yes, absolutely needed. Yeah, so this is preliminary data. We want to analyze this and see. Now, the key question is, because we design batteries ourselves, this is longer term. Can I design a battery so that when a fire takes place, that it's not spewing out such high levels, right, of the toxic materials especially? So can I integrate fire suppression in the battery design? Instead of being a runaway fire like it is, you saw in the South Korean parking lot or garage, can we do something that the fire even is self-contained to some degree, and so forth? So these are very feasible, and this is the merit of these. Of course, the first merit is the health of our first responders, firefighters, but then, hey, let's resolve this. And we put on our engineering hat to design that. So thank you very much. Hopefully this was of some interest, and the group is just fabulous. So I must acknowledge them once again. This is the current group. Keeps us young and exciting. I'll be very happy to answer any questions that you might have. Thank you.
Awesome. Thank you so much, Dr. Biswas. Really, really great presentation to see all the different projects and case studies that your team has been working on. So you do have a few questions that came through. So first one was, you mentioned you can put your aerosol sensors on drones. How do you take care of the issues caused by downdraft of the drone propellers? And does that affect the readings?
Right. So drones, you have to be very careful. For example, flying cars, even those have many sensors, of course, optical imaging sensors. But yeah, if you're trying to measure as a function of altitude, you have to be very careful. So the location of the sensor with respect to the flow patterns in the drone, and the drone might have propellers, you have to be very careful to design it. So there are a lot of folks who do aircraft measurements. There it's of course even more intense flow, and they actually design inlets and sampling systems for these, so they are readily available. The other thing I would say is, in contrast to drones, there are also certain balloon blimp technologies which are being used. There's a company right here we collaborate with, and we actually flew these blimps up. So if you want longer term altitude-based data, you would do that. But I presume this might be for a fire. You have to be very careful to design the placement, and those guiding principles are available, which I'm happy to share with anyone, or at least point out the reference where one can do that. So because you could fly the drone over the fire, and that is being done a lot with respect to the wildfires, at least in the West that I know of. Yeah. In California.
Great. Yeah, that's super interesting. And so maybe some area of collaboration and conversations that your team can have with the other scientists of our environmental sampling program, because they're also looking at different machinery and sensors. So it might be something, a good place for collaboration. Another question that came up is, what is the principle of your sensor where you can identify the composition of the chemicals in the aerosols?
Okay, we'll make another talk time when she is ready to earn her PhD. So like here, this sketch, I show you a laser and a particle in the center, the sample air coming in and it's scattering. And of course, there's a detector, right? And in this case, there's a mirror which sends the signal back to the detector. So by a laser here, I show you a red laser, but I can get a blue laser, I can get a green laser, I can literally choose any wavelength. So the wavelength of light is one very important parameter, and I can choose different wavelengths. The second factor is I can measure at different angles. Here I'm showing a 90-degree scattering angle, and I'm collecting over 30 degrees. I can have detectors all around it. And again, everyone is welcome to visit our lab. They'll see a prototype that Shruti is developing. So with multiple wavelengths and multiple angles, I get a very rich data set. We use machine learning algorithms and artificial intelligence-based neural networks to invert the data. So not only do I want to know the size and concentration, I get a parameter known as the refractive index. And with some pre-knowledge, so a virus, let's say, or a bacteria has a certain refractive index. With some knowledge, I can then say, okay, a fraction of these are that bacteria, or a fraction of these are a EV burn particle. It's a fitting algorithm still being developed, and that's how we do it. So it's multiple wavelength, multiple angle detection.
Amazing. All right. So I don't see any more questions in the chat, but really such a pleasure having you. Oh wait, someone else is coming through. One more before we close out. Were you able to determine concentrations of aerosols post-doffing? For example, what time frame before concentrations are lower than limits? And what distance do those DOF turnouts need to be from the rehabbing firefighters?
Right. So this is a very good question. And I didn't present that, of course. And I don't know if Shruti has done this measurement. So for example, this one, you want this to come down to background levels, right? And this is, of course, in the vehicle, but let's say in the chamber too. So we actually map that out, right? You can map it out, and we might have that data too. And with a given initial level, right, it also depends on the type of fire. For example, how long would it take to drop down to a certain level can be readily determined to give some pre-guidelines. But more importantly, if these variable things are on the individual, we can tell it real time for the exact scenario that the individual is in, like taking off the gear, right? And you then only take off the respiratory protection after it's come down to this background level, which is shown in the blue here. This is not a time-dependent thing, but yeah, we can get the time-dependent data too. And we might have some of that because that is clearly an important aspect, yeah. Mm-hmm.
Yeah, that's definitely something that our firefighters raise and questions that come up, in real life of how, far they should be away from the doffing gear when they're rehabbing. So really great information. So again, we are at time now. Dr. Biswas, thank you so much for your time and being here and presenting the work that your team has done. For everyone on the call, thank you again for joining our monthly seminar series. We are looking forward to our next seminar series. For September, Dr. David Lee will be presenting on some of the work that our cancer surveillance and epidemiologic team have been doing. So we're looking forward to that. If you guys have any questions regarding any of the presentations or anything that is happening with FCI, always feel free to reach out to us, either our direct emails or the firefighterstudy@miami.edu. So thank you all and have a great rest of the week. Take care.
Great. And anyone have questions, they can email me too. I'm open to answering later too. Thank you. Thank you. It was a great pleasure speaking.
Take care, everyone.